Hey again, everybody. So it looks like with this video, we're going to be able to wrap up our image pre-processing. So if you think back to all of the different things we had to do after acquiring that raw DN data from our sensor, at this point we really do have an image that we should be able to work with for our classification or our biophysical modeling or whatever analysis we want to do. But often you'd like to take one additional step to see if there's any way that you can enhance the information that's in your file to make it easier to accomplish whatever it is your ultimate analytical goal is. And so we refer to this as digital image enhancement, and it comes in a couple of different flavors. If we're talking about spectral enhancement, that's basically any step you might take to either isolate important information within the spectra itself, right? So within the band data, or any way that you can remove noise that might be in the spectra so that you're really isolating just the signal that's of interest to you. And there are a couple of different techniques you can use to do that, to enhance your spectra. There's also radiometric enhancement, and really this is mostly so that we can make sure that the histogram, if you look at the lowest value for a given band and the highest value, that histogram stretch is sufficient so that we can really see distinction between different land surface features, right? If they're all pretty much bunched around the same data value, it's going to be hard for us to distinguish between different objects. And so we can try different types of contrast stretching to really tease out and differentiate different objects. And sometimes we want to link together multiple images. And if they're acquired on different days or even at different view angles, they often can just inherently have different brightness. So we also might want to think about histogram matching between two different images. And then there's a whole class of spatial enhancements where you can try to either refine or improve the spatial resolution of your imagery, see more detail, sort of sharpen what you're looking at, or you can sometimes actually degrade the image. Sometimes you want to resample the imagery so that the resolution of whatever your imagery is matches some other data layer. Sometimes there's so much noise in your data that you would like to smooth it out and sort of get rid of some of those, just that sort of random variability across the image. So those are different spatial enhancement tools, and we'll just talk briefly about each of these. The overall goal, no matter which of those we decide we need to do, is to improve our ability to be able to distinguish between features in the image. And we've seen that when we opened up some of our images in Envy. You may have noticed that they seemed rather washed out or really dark. They just didn't look right. I'm sure this concept isn't new to you if you think about Photoshop, but it's also used in a lot of different scientific applications, the same approach. And, one of my favorites, there are scientists who use near-infrared spectroscopies to identify text in these ancient documents. In particular, this one was the Dead Sea Scrolls. So it's very interesting to think that they have these sort of degraded pieces of really lambskin, I believe is what they were primarily recorded on, and they can start to adjust the resolution and look at these with different wavelengths and begin to see more information. This is exactly what we want to try to do. Whatever it is we're trying to identify, we want to be able to use these enhancement techniques to pull out that information. The simplest enhancements really don't change the actual data values in the image at all. It's just changing how you're viewing the image. And that could be as straightforward as just selecting a different set of bands to apply to your color guns for viewing the image. Another example of a strictly visual enhancement, again, meaning that we're not changing the data values, is how we can adjust that contrast stretch within our image to be able to see things more clearly. And it literally is a very simple process. What we have is the histogram for our original image. So this is literally right out of the statistics file for that image for a given band. And what we can do is we can actually convert this actual data, these actual values, to a lookup table that applies them over the full range of your radiometric resolution. Remember, if you're 8-bit data, you have 256 possible values from 0 to 255. And so a lookup table can be used to basically stretch that range that we truly have in our data across a wider range of values. And this helps us really to increase the contrast and identify different features. Typically, contrast stretching is done just to improve the visual appearance of our images, but histogram matching essentially does the same thing, but this time instead of just changing how those digital numbers are viewed on the screen, it actually changes the values in a file. So when we're doing a histogram match, we would pick one image as a base image, and the other one we would mathematically adjust so that its histogram matched the range, and in terms of both the minimum and the maximum, but also as in terms of the full stretch between the two, so that when you are either mosaicing two different images together, or if you're trying to make sure that the brightness is similar for two different images from different dates, it helps you to make sure that you're controlling for just those inherent differences that have to do with general illumination rather than true differences between the scenes. And it certainly helps to make these images look like they belong together, like they fit. And just to give you an example of how this works, what I have here are some hyperspectral images from an aerial platform. So you can see the plane was flying down this path, and then it came back up this one, and so on and so forth. And because the illumination was slightly different and the view angle from the instrument itself was slightly different, you can already see how some of these images are brighter than others. And so if we wanted to now take these different flight lines and mosaic them together into one seamless image, we'd have to make sure that we were matching those histograms first. Otherwise, what we'd see is really just what would look like a very obvious patchwork with striping. So in Envy, when I'm running my mosaic, I can actually specify which of these images I want to be held or fixed as the base, and then I can adjust the other two. I can edit the entry and make sure that the other ones are being adjusted and that the data value to ignore is 0, so that it knows to let the other image values show through wherever there's a 0 in the images that are above. And so now you can see I've got my two images being adjusted to that one in the middle. Before we run the mosaic, we specify where we want those statistics to be pulled from. So if it's trying to match the histograms, it gives you options of either looking at the histogram only from the pixels where the two images overlap, so that you know you're comparing apples to apples, or you can compare the statistics, the histograms, from the complete image. We usually like to go with just the overlapping regions if we have sufficient coverage. So now, when we look at the finished mosaic, it's very difficult to see where those images end and the others begin. And just to give you an idea of how different they were before, we've decided to match those histograms so they have the same brightness, and that does make it much more seamless for us. In addition to spectral enhancements, we can also do spatial enhancements, which are essentially trying to alter how much variability or contrast there is in an image to either accomplish one of two things: to either smooth out the image, or we can actually try to sharpen the distinction between features. And we refer to these as either a low frequency or a high frequency adjustment. And we'll see filters called low pass filters and high pass filters. If we're running a low pass filter for low frequency data, we're essentially trying to smooth out those differences between pixels so that we're really making an image that doesn't have as images that are quite as crisp. But the high pass filter for high frequency data is really trying to make that brightness contrast show up even more distinctly so that we can really identify edges. These spatial enhancements are accomplished just by using what we call a moving window filter. So you first can specify the size of this moving window, and it starts in the very upper left pixel of your image, and it can do different mathematical algorithms depending on what you're trying to accomplish. But essentially you're taking all of these surrounding values and you're using that information to change the pixel value in the center, and then the entire window moves over 1 pixel and does the exact same thing for the next pixel in the image, and so on and so forth. This window keeps moving until every pixel now has a new value. And I'll give you an example of some of these different spatial filters. Remember that low pass filter to make low frequency data is really meant to smooth out the contrast. So it sort of mathematically makes sense then that if you just took your original DN values from your image and you applied a filter where every single one of the pixels in that window were weighted equally, and just report the mean in the center. And so now for this first window position, you end up with a new value of 4 in that center pixel. Right now everything else has stayed the same because the filter, the moving window, hasn't moved to those pixels yet. But you can see how before the contrast here between this 8 value and its neighboring pixels was much greater than the contrast now. So in essence, this has made this 1 pixel a lot less bright relative to its neighbors. So again, this is the low pass filter, and we use this to smooth out data and reduce that contrast in our images. And often this is really useful when you have highly variable, very noisy data, and you're really interested in sort of larger object identification, and so you'd like to maybe get rid of some of those little noise, pieces of noise in the image. And what does this look like? Well, as you can imagine, it's essentially like taking your image and making the whole thing more blurry, because essentially you're averaging it all out. And it seems silly, why would we ever do this? But if you look closely, you can see some artifacts in here. So for example, look in this section here and you can see some darker pixels in the middle. If this is something that you really didn't want to classify out, you could apply this low pass filter and now have a much more homogeneous object on the ground. So remember, I pointed out that there are lots of different specific weightings or different algorithms that you can use to accomplish different things, slightly different results. This is another example of a low pass filter that was used to smooth an image, but they didn't necessarily want to lose so much of the contrast as much as they just wanted to eliminate, some of these artifacts in here, these sort of scraggly lines. And so instead of the mean, they would just use the median for that center pixel. So let's take that same initial satellite imagery in our moving window, but if we were interested in actually emphasizing the differences and the edges within our image, we might want to conduct a high pass filter. And what this one does is it actually gives a very heavy weighting to that center pixel value, the one that it's trying to replace, but it actually weights in the other direction, the surrounding pixels. So essentially it's trying to say, we want you to increase this one, but decrease it based on the weight of all of the other ones, essentially trying to enhance any edges that might be apparent within the imagery. Right? And so when you apply this weighting, you end up with a very different value in there. To give you an example of what that high pass filter looks like, here's our original 10-meter spot imagery, and we haven't changed the spatial resolution at all. This is still 10-meter imagery, but we can see much more clearly the edges of each of these features. So if we were trying to digitize, for example, different objects, this might be something that we would want to do first as an enhancement. In addition to changing the weightings or the type of algorithm that you use in that moving window filter, you can also actually change the size of the window itself. And so for that low pass filter, as you increase this moving window size, it takes an average over a larger and larger area and leads to even more extreme smoothing. Now for the high pass filter, the kernel size, again the moving window, the size of our moving window, also impacts our edge detection. And essentially the larger the window, the more distinct the edges will be, because it's again taking a contrast over a larger area, but it's actually making it so that you won't see any edges of small features. So it's really helping you identify features of a particular size. If I was interested in identifying edges of larger areas, I might choose to have a larger kernel or window. If I really were interested in those smaller features, then I would want to have a smaller window to be able to use. Just to give you an example, we have some really high spatial resolution imagery here, which even after we run that 3x3 low pass filter to smooth, we still see quite a bit of noise in here. When the computer looks at this, it sees some edge with just a whole bunch of different things in there, right? There's some that are blue, there's some that are black. So if we wanted to actually smooth this out so that it might be more easily identifiable as one object, we could run a larger 7x7 window. And now there's not quite as much noise within this. I mean, you can even see that in the highways too. This larger window smooths over a larger area so that it's easier for us to see features like that, whereas before they really were spotty and mixed with other surface types. And similarly, it's going to impact our high-pass filters as well. If we had an image like this one and we really just wanted to identify the edges or the boundaries of these different surface features, we could try one size window, and if it really isn't showing us, I mean, to me this is really kind of washed out. If it isn't showing us as much of those edges as we want, we can take that window even larger and see if that helps. And again, we might lose some of those small edges, those smaller features, but boy, does it really make these larger features much more distinct. So we talked about how you can do either a low-pass filter, which takes averages and reports them at the center, or you can do a high-pass filter, which actually tries to increase the contrast between that center pixel and its surrounding pixels by weighting them in opposite signs. But there are other options too with how you can arrange these weighting algorithms, and I'd like to introduce you just to some of the more common ones so you can understand how they're different. One really common example is what we call a ZeroSum filter, and what this means is that when you take the contrast between that center pixel and all of its surrounding pixels, they'll always sum to 0. And what does is it increases the contrast without actually changing the histogram itself, because all of these weightings will ultimately, as this window moves across the image, always average out to the same value for the whole image. So it doesn't change our global histogram. This type of a filter does help us identify edges a little more clearly. For example, look at the edges for this field here and how easy that is to see compared to over here. But it doesn't change the overall histogram. It's really amazing how changing things just a little can make such a difference in your image. If we were to use a OneSum filter instead of a ZeroSum filter, what we're doing is we're essentially making it so that all of the coefficients with their weightings in this moving window sum to 1. So notice that now instead of having the center pixel being weighted with the value of 8, it's actually being weighted with the value of 9. And what this does is it essentially leaves you with just the edges, and it takes all of the pixel values out for the rest of the image. So this is, not just a cool way to make pretty pictures, but this might be useful to you if you really just wanted to isolate the edges that you could then use in a subsequent analysis, like a spatial analysis. Another common type of spatial enhancement is not just working with the pixel data that you have, but it's actually merging two different images of different spatial resolutions. And this is most common when you have an instrument that includes a panchromatic band, one extra band tacked on there that covers the entire visible spectrum. And because this band is much wider, you're actually able to have a smaller pixel size but still return enough spectral signal to have useful information. And so if you have one of these panchromatic bands, you can use that band to sharpen the other bands within your image. This is also really common when we're trying to fuse data from different sensors. You need to make sure that they're all in the same resolution so that they are comparing apples to apples. Here's an example of that pan sharpening when we take that one band panchromatic band that says 1 by 1 meter resolution, which is a much higher spatial resolution than the 4 meter multispectral data, but we can use this panchromatic band and essentially multiply the brightness value from each of these 1 by 1 meter pixels with the value from the 4 by 4 meter pixel to really increase the spatial resolution, along with having the spectral resolution that's in the 4 by 4 meter imagery. Let me try to give you an example of how this works. So you have your lower resolution multispectral data. So imagine this is your 4 by 4 meter data. And then you have your 1 by 1 meter panchromatic band thrown in there. It literally overlays them on top of each other and just takes the average between those two so that you end up with now a 1 by 1 meter resolution image that's been weighted by the brightness value of that panchromatic band. So obviously the key to this, if you're going to be overlaying these two images, is to make sure that they're co-registered well, right? That your geometric correction and the registration between these two images is highly accurate. I'll give you another example of this in action. I think it's a lot clearer when you can see the original multispectral 4 by 4 meter pixel up against that panchromatic band with the 1 by 1 meter pixel. So essentially when you're taking this image, but you're using this one to sharpen it, you end up with an output image that has this 1 by 1 meter resolution, but also now has the multispectral information that you need to do most of your classification. Just like with our different filters for our spatial enhancements, the low pass or the high pass filter, and all the different custom filters that you could create, there are also different ways that you can do these resolution merges. The example I gave you before was just taking a straight average, right? So you would have a larger pixel size multispectral image, and you would just take its corresponding panchromatic band value, and you would multiply that back and take an average. So now you would have this higher spatial resolution with the average of its original larger pixel value times the brightness value for that smaller, higher resolution pixel. But there are other ways mathematically that you can get at that average. And one example of that is a Brovie merge. So instead of just taking the straight average, what the Brovie merge actually does is it takes that value for each band, but it divides it by all of the other bands. So it's actually taking into account the values for every band within the image, and then it multiplies that by the panchromatic band value. And it will do that for each of those bands. So in this way, you're actually making sure that all of the information from the other bands is also captured rather than just being entirely washed out by this full visible spectrum panchromatic band. Other resolution merge options are even more complex, and an example of that is a principal component method. So we've talked before about how you can perform a principal components analysis to take your original bands and essentially rearrange them into a new set of bands to maximize the variability in your pixels so that you can really identify different features clearly. And so what you would do in a principal components resolution merge is you would take this new principal components analysis image, and you would take that very first principal components band and just throw it away and replace it with the panchromatic band. And so now when you bring this panchromatic band back in and you retransform that data, you end up with an image that no longer has any of its sort of original color values, but it is sharpened and enhancing the spatial variability based on that principal components analysis transform that you've completed. Enhancements are usually pretty fun, and there's no one right type of enhancement to use. Really, you have to figure out, again, what your ultimate objective is, and then think about which different techniques might help you to achieve that. And so sometimes you might end up trying several different enhancements until you find the one that works best for you. We'll be working in Imagine this week for lab, playing with some of these different enhancement tools. Some of them are really pretty straightforward. For example, we were talking about at the beginning of this lecture, the the contrast stretch, which really just changes how we visualize our imagery. So if I go up to the multispectral tab here, I can see this adjust radiometry tab, which gives me all sorts of different options for stretching or enhancing the spectral values of my imagery. But what's really great is that in terms of just the contrast stretching, it already gives me a whole bunch of options right here. And just by simply hovering over each of these little snips of my image, it shows me how each of these different mathematical contrast stretches alters what my image looks like. So you'll be playing with that and trying to decide which of those you like best. We'll also be looking at some of the spatial enhancement options that are available to us in Imagine. And you can see there's quite a bunch of different filters that we can be using, these different convolution filters. And we can even make our own custom filters and then also try pan sharpening, which will allow us to take this panchromatic image that we have and use that to actually make a new multispectral image that has that 1 meter resolution. And we'll try a couple of these different techniques so that you can get an idea of how these different enhancements work and what they can do to help us with our image analysis. Should be a fun lab, and I actually think it'll be pretty quick. So I'll let you get to it, enjoy the quiz, and I will see you in lab